All right, welcome to the third part in this video series. We previously talked about stress and what defines stress, and we looked at the 3D Cauchy Stress Tensor. And now I would like to look at the 2D Cauchy Stress Tensor for the purposes of explaining what principal stresses are and why principal stress is important. So if you have, I have over here the 2D Cauchy Stress Tensor defined, and you can define it by three states of stress. Again, because the shear stress xy is equal to the shear stress yx. And so you can calculate the principal stress. The principal stress is essentially the eigenvalues of the 2D Cauchy stress tensor. And the eigenvectors are going to define the directions or in which the principal stresses act. So if you remember from linear algebra, if you want to find the eigenvalues of a matrix, you set the you find the determinant of the matrix A minus the eigenvalue times the identity matrix, and you set that equal to 0. And so I've shown the equation here if you do that out, and I plug the stresses in, and we arrive at the common equation for the principal stresses. And if you plot this, if you plot this function right here, you'll actually get Moore's circle. So this is how Moore's circle was essentially derived. And there's a 4 here, and typically you'll see this as over 2 squared, but the 4 is outside the square. So typically you'll see this inside the square, and then it's the normal, the x normal stress minus the normal y stress over 2 squared. And so what the principal stresses are, I guess I'll explain it by saying there exists a coordinate system as defined by the eigenvectors, where if you look at the stresses in along those axes as defined by the eigenvectors, there will exist a state where the shear stress is 0, and the stress is only acting in those principal directions. All right, so now I'll talk a little bit more about the principal stresses in the 2D stress state. So previously we learned that the principal stresses are the stresses that act in the direction of the eigenvectors. And to determine the coordinate system that you have to rotate, or determine the angle theta that you need to rotate the base coordinate system in to align with the principal stresses, you can actually calculate that. And I've shown it here, theta p, 1/2 the arctan of 2 times the shear stress divided by the difference of the normal and the normal x stress and the normal y stress. And so basically what that means is if you take a coordinate system and you rotate it relative to the original coordinate system by angle theta p, you will end up, and you look at the stress in, let's say, the y prime direction, that will correspond to one principal stress. And then if you look at the stress in the x prime direction, that will correspond to the second principal stress. And in this state, in this coordinate system, I should say, the shear stress would be equal to 0. Now, that doesn't mean that the shear stress in your part is 0. What it means is that there is a coordinate system as defined by the eigenvectors where the shear stress is 0. And the principal stresses act only in the eigenvectors, or as defined by the eigenvectors. Now, the reason why principal stresses are so important is because how they relate to failure analysis. So typically, if you were to do, let's say, a tensile test, and you applied a load until failure, you will find that the failure occurs along the maximum shear plane, or the shear stress, or the max shear stress, and that's defined by the principal stresses. So the max shear stress in is the maximum principal stress minus the minimum principal stress divided by 2. And in a 2D state, that acts at a 45-degree angle relative to one of the axes as defined by the eigenvector. So it's important to be able to calculate the principal stresses in order to find the max shear stress. Also, when you learn about failure analysis and crack propagation, the principal stress is very important to calculate and understand the directions that they act on, because cracks will propagate relative to the principal stress directions, and depending on the material and how the crack originates. And there's a few different modes of crack propagation. But in order to calculate all that, you need to be able to calculate the principal stresses, um, for that analysis.